Hello potential KNX developers, my name is Matija Marasic, and on behalf of the developing department of firma Tapko Technologies, my colleague Zlatan Živković and I will try to present our company and the development with our case stack. Tapko Technologies was established in 1999 by Mr. Klaus Adler and Peter Tomic, who were both among driving forces of the KNX EIB even 10 years before the company was established. Principal office is located in Regensburg, which is a cradle of the KNX and EIB. It's a German city between Munich and Nürnberg, and it's easily accessible from both airports. Our subsidiary manufacturing company Apricum TOO was established in 2001 by Ms. Olivera Tomic, and it's located in Split, Croatia. Our second subsidiary company, Tapko Tech, was established in 2011 by firma Tapko and Mr. Christian Gosset. It is located in Alsace, France, near Strasbourg. Tapko is employing around 20 people, and it's constantly growing together with its subsidiary companies, Apricum and Tapko Tech. For example, Apricum now reached level of producing roughly 6,000 KNX devices per month. Our company offers wide range of services that include development, OEM products, manufacturing, KNX stack, support on any KNX issues, and the KNX test lab.
So thank you, Matija, and now I want to introduce myself. I'm Zlatan, and I'm a software engineer in firma Tapko. Now we will talk something about our KNX communication stack. Our stack is a super modular stack. It's assembled from various different parts, which are modularly connected and super user-friendly. Our stack is made in universal way that you can make everything that you want.
So the modularity enables you to choose the components that you need and assemble product that fits your requirements.
Our stack enables customers to develop any kind of applications on any kind of platform and any kind of hardware that you want, with various possibilities and various modules that you can include. With this stack, our company offers also a wide range of eval boards on which you can develop everything you need. On our website you can find all our free available KStack software with appropriate documentation. Today I'm going to show you how to develop a simple application with KStack on Tapko eval board. So let's go down to code. Our software on all our devices always behaves in the same way. After the power up, the software initializes the stack and then the application, and then after that you have a cyclic loop in which all the cyclic processes are called. Our software is also event driven, so when there is nothing to do, the complete system can just go in some kind of a power down mode. Now I'm going to present you a development of a very simple application in the KNX world. This application is called Echo application. This means it has two objects, one for input, one for output. All the values received from the input side are after some delay time inverted and sent on the output side. Also the working state of this application you can see with a toggled LED on the KNX board. After installing the KStack demo software with default settings, you will find everything extracted in your C drive at KStack demo STM32 GCC. you can see the structure of our stack. We have a few folders. One is a system folder where you can find all the files which are related to the KNX stack system. Now I want to show you how to create an application. Just start the application wizard, and now you can put in your name of the project, your project folder, select target microcontroller, some device model, and a physical layer you want to use. If I click generate, you will see that we have now an application folder, and inside we have a folder Hello KNX, so that's our application. If we enter inside, you can see a few different folders. You can see that we have a source folder where the source files are located. We have also some temporary folders for building process, some dummy folders for ETS export, some workspace folder which holds some environment related things. Outside we have a build command and rebuild command, so you can build our stack from any kind of environment or shell or directly here from the browser. I want to show you also, here we have a complete mbits project which is created together with this folder. We open this project. You can see that we have exactly the same structure, same files as the source files. So here are the source files. Here it is inside the project itself. We have also some make files where you can place your files inside. And now I want to explain you the structure of our project. Now first, to check what we have to do. In our slides we have an image which shows us two communication objects and one ETS parameter delay time. Communication objects are defined in our cotab.h. So this means communication object table header. There we already have one object defined, and now we want to define our output object. Our output object, I will just copy it to save some time. So here we have the name of our object. There we can place CO out 0. We have also the connection to our group address. So this is a connection through the association table, and we can connect it to some different group address, let's say 201. Now we have some reference to some RAM value which we will use with this object, and there we can fill it with out 0. This will be shown later where this out 0 variable should be placed. We have some object type, some DPT value for ETS export, and now we have some kind of a communication flags. This one we have to fill it so that we are able to transmit our object over bus. So we can say it is readable from the bus and we are able to transmit it. Our input object, so this upper one, has also the flags for writing and updating. So you are able to write it from the bus and update it from the bus. All these definitions you can find in our documentation or also in this file, in this upper part of the file. We also have some kind of a priority, and this priority is currently set to low. The other thing we have to do is increase the address table length, because now we have two addresses, and also the association table length, because there are apparently two associations, two objects with two addresses. The individual address of the device you can change if you want, but currently we will leave it as it is. And that's it for this file. Now we can go to application header, because all these parameters are referencing some structures in application header. There you have the maximum application address table size, which is currently set to 30. We can leave it as it is. The same is for association table size, but the object table size we have to increase to 2, because we have now 2 objects. This is our structure for saving the values from the objects. There we need to add one more object, which will be called output object. So the value for this output object we will save in some RAM variable out0, which we are referencing also in our CO tab at the end. So here. And that's all we need here. We also need one parameter. Currently we have here some dummy parameter. We can exchange it with some kind of a delay time. This one we will also need for our ETS export, but that we will see later. Now we want to go to define the initial values for the objects and for the parameters. That we can do in application data.c. There we have already the ETS parameter export, but it was for dummy parameters, so we will put it to some kind of a delay time. Just copy it here. User objects we are currently not using, and we can put some delay time of, let's say, 1 second. Just rename it here, delay time. Now we can see that everything what is compiled here through this application data.c. Here we have a reference to our cotab.h, where we filled our communication object table. The only thing left now is our functionality. So what do we do with these objects? According to our presentation, we have to, after receiving the input object, wait for some delay time and then send an inverted value through some output object. So this would mean that on the address 200, which we defined in our communication table object, we will receive one value, some boolean value, so this is dpt1, and we will invert this boolean value and send it out through object which is currently associated with address 201. So let's make this functionality. In our hello KNX.c, this is our main file for our main application, we have different procedures. We have some hardware init and hardware cycle, which are executed always. So hardware init is executed once at the beginning at the initialization, and application hardware cycle is executed wherever you need it. These two are always running, so no matter if the application is loaded or not loaded, application hardware cycle is always called. All of this is event driven, so we can just make it cyclic driven if we add this one command, so if we really need it. The main thing where we want our application process to take place is in another part, which is up init and up main. These two are called only when application is loaded by the ATS. So in application init, we have to first initialize our object so that they don't have some kind of a random values. This we can do with just typing object value pointer to our RAM variable, so to the value of the object in 0, let's say equals 0. So this is our initialization. In the main cycle, what we want to do is we want to check this communication object, so communication object 0, and just start some kind of a delay for now. Yeah. So if check update flag on our communication object, which we can copy from here, so 0 in 0, and now just tm start timer some kind of a user timer. You can name it whatever you want. It's just important that you have it somewhere defined. In our case it is in project.h. We have it here defined as okay, application header h. So we have 4 timers, which 3 are used on the system and 1 is used by the user. We can use this kind of name, we can name it whatever we want. So let's say we start this timer and we started with some kind of a parameter. So to access the parameters we have to write, let's say, parameter dot, and now our name of the parameter. We have currently made a parameter which is called delay time. So our parameter delay time. Now, because of the Indians issue, we can simply rotate the value of the delay time inside the memory. So we can use get integer and just put here the delay time. We have to fill up also the mode. So the mode of the timer, this you can find in our documentation. Like all of these things that I'm doing currently, we want it that this parameter is used like 1 second parameter. So timer mode 1 second. So this would mean that this default setting here, int const from 1, should be a delay of 1 second. The next thing we want to do is we want to check if the timer has elapsed. And so like in this presentation, if the timer here has elapsed, then we want to invert the value and send it out on the second object. So if timer gets date from user timer, then we want to fill up the object value from the output object. Out 0, which we have, and we want to fill it with object value in 0, but inverted. So we can use something like this to make it a bit more understandable. Now we have our value stored in object value output. We can now just set transmit request so that this object value exits out on the KNX bus. Here we have to use our object name, which you have placed inside the communication object table list. And now this should be our functionality. So we receive some object, we start the timer with the parameter delay time, and then in the cycle we just check our user timer if it has elapsed. If it has elapsed, we set the output object value to inverted value of the input object and just send out the output object. This is it regarding the application functionality. We can now try to compile it. First time we need to use rebuild to make all the folders. You can see now that this command from the environment calls our make process in behind. So here we see some compiling process, some make file specific process, some linking, and there you see an output. And now you see also the ETS conversion. So for this ETS conversion we get some kind of an ETS files. Let's see now what we have here. So in this output we have our files, which are executable files, also some hex files, some map file that you can see where everything is placed, and we have some files which are helpful for manufacturing tools import. We can do one more thing just for fun. We can make one user LED blink, let's say on each received object. So the user LEDs from our eval board you can initialize with the functions beginning with KSD, init user LED. You have the same functions for buttons also. We can place this also in hardware init, but it it is not necessary. In application main, on each received input object, we can, let's say, toggle the LED or just place it with the value of the input object or something like this. I can call this one as an switch user LED. And just place here object value, let's say this input object. Now we can rebuild it again. Have some errors here. Yeah, one bracket too much. And keyboard failure. Of course, we want to name which LED we want. So let's say here we want to use it like this. And that's it. Now we should have it working. Before you start debugging, you may check your interfaces. Let's say GDB server, that it is set to ST-Link and that it is set to load the program. Here you can use serial wire debugger or JTAG if your microcontroller supports JTAG. In target settings, we can say run to main, and that's it. Now start the debugging session. You can see program is loaded to the microcontroller and our program stops at main. If we run it, now we can play with an ETS to check what happens. Now let's see it in ETS, how our program is working. So open the group monitor. In group monitor you can place some kind of a group address. So there we will place our input object address 200 and start the group monitor, which I already did. Just type switch on, off, I don't know, let's say switch on, and right. We immediately see that after 1 second our response came and our LED is on. We can also write off and we see the same reaction, just the LED is off. You can also see that the values are inverted, so we send on and the value returned is off. The same thing is for the second try. And that's it. We have a working KNX application.